Since the Clausius inequality is a mathematical formulation of the second law of thermodynamics, it can also be used to introduce a new thermodynamic function called entropy and reformulate the mathematical expression of the second law. Let us assume that a thermodynamic system depicted in the pressure-volume diagram evolves from the state A to the state B along a path represented by the curve C1, and then it is brought back to its initial state A along another path represented by the curve C2 in a reversible thermodynamic cycle. Then the Clausius inequality states that the cyclic integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed in the reversible process vanishes. We can break up the cyclic integral into a sum of a line integral along the path C1 from the state A to the state B, and a line integral along the path C2 from the state B to the state A. Since we can reverse the orientation of the second line integral along the curve C2, the integral of the reduced heat along the path C1 from the state A to the state B is equal to the integral of the reduced heat along the path C2 from the state A to the state B. In other words, the integral of the reduced heat depends only on the initial state A and the final state B, and is independent of the path along which the reversible process takes place between the states A and B. Since the initial state A and the final state B of the process are completely determined by the state variables of the thermodynamic system describing those states, the line integral of the reduced heat of the system is also a unique function of the state variables describing the states A and B. Motivated by this fact, Clausius introduced a new state function, that is a thermodynamic function depending only on the state of a system like its internal energy or its enthalpy. This state function is called the entropy S of a thermodynamic system, and it is defined as follows. The difference between the entropy S of the system and the states B and A is given by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed by the system along an arbitrary path in a reversible process between the states A and B. This definition shows that the unit of entropy is the ratio of the unit of heat to the unit of absolute temperature. In SI, the unit of entropy is joule per Kelvin. The only issue with this definition is that thermodynamic processes in nature are always irreversible in a strict sense, and they cannot be applied in the determination of the entropy difference in the definition. However, if we consider the idealized limiting case of quasi-static reversible processes bringing the system from the state A to the state B, that can be used to determine the difference between the entropy of a thermodynamic system in two different states. Like internal energy, entropy is defined up to an arbitrary additive constant. The value of entropy can therefore be chosen as 0 in an arbitrary state P0, and the entropy S of a thermodynamic system in the state P is defined by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed in a reversible process, from the null state P0 to the state P along any path represented by the curve C in the state space of the system. As in the case of the definition of the change in entropy, this definition shows that the unit of entropy is given by the ratio of the unit of heat to the unit of absolute temperature, and its SI unit is joule per Kelvin. An equivalent definition of entropy can also be given in the following form. If a thermodynamic system absorbs the infinitesimal amount of heat Q rev at the temperature T in a reversible process, then the infinitesimal change in the entropy S of the system is equal to the ratio of the absorbed heat dQ rev to the temperature T. We saw that entropy is a state function, that is the line integral of the reduced heat in the right-hand side of the previous definition of entropy depends only on the initial and final points of the path of integration, but it is independent of the path. As a result, the left-hand side of this definition is an exact differential, namely the exact differential of the entropy S. Then we can rephrase the first two theorems of thermodynamics in differential form. The first law states that the infinitesimal change in the internal energy U of a system is equal to the infinitesimal amount of heat Q exchanged between the system and its surroundings, plus the infinitesimal work W done in the process of heat exchange. The second law states that the infinitesimal change in the entropy S of the system given by the ratio of the infinitesimal amount of heat Q rev absorbed by the system in a reversible process to the temperature T of the system, is an exact differential. The definition of entropy given by the integral of the reduced heat of a thermodynamic system in a reversible process is formally equivalent to the definition of the potential energy of a mass point moving in a conservative force field. We saw that the entropy S of a thermodynamic system in the state P is defined by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed by the system along any reversible path calligraphic P from a null state P0 to the state P in the state space of the system. In dynamics, the potential energy E pot of a point mass moving under the influence of a conservative force F at an instantaneous position P is defined by minus the line integral of the force field F with respect to the arc length S along an arbitrary path calligraphic P from the point P0 representing a null point to the point P. Based on the definition applying the integral of reduced heat, we define the differential of entropy S by the ratio of an infinitesimal amount of heat Q rev absorbed during an infinitesimal reversible change in the state of the system, to the temperature T of the system. As a result, we saw that the infinitesimal change of the entropy is an exact differential. Similarly, this definition is equivalent to the statement that the differential of the potential energy E pot of a point mass is given by minus the scalar product of the conservative force F acting on the point mass and the infinitesimal displacement ds of the point mass. The infinitesimal change in the potential energy is therefore an exact differential. If a reversible process is adiabatic, that is, no heat is exchanged between the thermodynamic system and its surroundings, then the differential of Q rev vanishes. By applying the integral definition of the entropy S, we can conclude that the difference of entropy between the states P and P0 also vanishes. If P0 is a null state, then the entropy is identically zero. The differential of the entropy S vanishes as well, and both the equations show that the change in entropy is zero. In other words, the entropy S of a system is constant during a reversible adiabatic process. We call any process with constant entropy isentropic process, and we can conclude that reversible adiabatic processes are isentropic processes. In the case of a conservative force F acting on a point mass, we can talk about the motion over equipotential surfaces defined by the vanishing scalar product of the force F and the infinitesimal displacement ds of the point mass. That is, any displacement perpendicular to the force F is over an equipotential surface, where the difference in the potential energy E pot of the point mass between the point P and the point P0 vanishes. Since P0 is a null point, the potential energy is zero for the motion along the equipotential surface. Then the differential of the potential energy vanishes as well, that is, E pot is constant during the motion, as the name of the equipotential surface indicates. As a result, we can state that the potential energy of a point mass is constant while it moves over an equipotential surface of a conservative force field. All these statements show an analogy between reversible processes and conservative forces. We applied the Clausius inequality to introduce the concept of entropy, and we can also use it to study the principle of entropy production. Let us consider a thermodynamic system evolving from the initial state A to the state B in an irreversible process along a path represented by the curve CR in the pressure volume diagram. Then it is brought back to the state A along a different path represented by the curve C rev in a reversible process. As a result, we can talk about an irreversible thermodynamic cycle where the Clausius inequality holds, that is, the cyclic integral of the reduced heat of the system is strictly less than zero. Now we decompose the cyclic integral into the sum of integrations performed along the irreversible and reversible paths. Here the direction of the process along the individual paths is indicated by the superscripts of the curve CR and CR. Then we state that the integral of the reduced heat of the system between the states A and B in the irreversible process, plus the integral of the reduced heat between the states B and A in the reversible process is less than zero. If we apply the definition of entropy, then we see that the second integral along the reversible path in the left-hand side of the inequality is simply equal to the difference in the entropy S between the states A and B. By reordering the terms, we can write that the difference in the entropy S of the system between its states B and A is greater than the integral of the reduced heat of the system along an irreversible path between the states A and B. In other words, the increase in entropy, that is the production of entropy, is always greater than the sum or the integral of the reduced heat of the system in an irreversible process. Let us suppose that the thermodynamic system is isolated and there is no exchange of energy between the system and its surroundings. A non-isolated system can be made isolated by supplementing the system with the bodies interacting with it. Since no heat is exchanged in the case of an isolated system, even the infinitesimal change Q in the heat is zero. As a result, the integral of the reduced heat of the closed system vanishes, and we can write that the difference in the entropy S of the system between the states B and A is greater than zero. Then we conclude that the entropy of an isolated system increases during an irreversible process in the system. In the idealistic limiting case of reversible processes, the entropy of an isolated system is constant. Therefore, the change delta S in entropy is never negative in an isolated system. This is the principle of entropy production, which is one of the most important form of the second law of thermodynamics. This principle tells us that thermodynamic processes can only take place in an isolated system until the entropy of the system reaches its maximum, as it can be seen from the following arguments. If the entropy of an isolated system has maximum, then we have two possibilities. Either the state of the system does not change anymore and the system is in thermodynamic equilibrium, or any further transformation of the state of the system is a reversible process with constant entropy. However, reversible processes represent the limit of an infinite number of successive equilibrium states during the transformation of the state of a system, which is just an idealized case and does not occur in nature. As a result, the principle of entropy production involves that an isolated system has maximum entropy in thermodynamic equilibrium. Let us suppose that an isolated system evolves from the initial state A to the final state B along the path P in the n-dimensional state space of the system. If the entropy of the system reaches its maximum at the state B, then the entropy increases along the path P. Since entropy is a state function, it is a unique function of the state vector x of the system combined from the state variables x1, x2, ellipsis, xn of the system. An infinitesimal change in the entropy S is greater than or equal to 0, and its differential can be expressed in the terms of its partial derivatives with respect to the state variables xi. As a result, the sum of the product of the partial derivatives of entropy and the differentials of the state variables must be non-negative, but the principle does not generally provide conditions for the partial derivatives themselves. We consider Joule's free expansion experiment as an example. It is an irreversible adiabatic process in which an ideal gas expands into an insulated evacuated chamber, and it could be approximated as an isothermal process due to the negligible difference in the gas temperature measured before and after its expansion. Then the isothermal expansion of the gas in its state space, that is in its pressure-volume temperature diagram, is represented by the path calligraphic P between the initial state A and the final state B along one of the isotherm. For any infinitesimal displacement along the path calligraphic P, the differential of the temperature T vanishes, the differential of the volume V is positive and the differential of the pressure P is negative. Then we have only a criterion stating that the partial derivative of the entropy S of the gas with respect to its volume V times dV must be greater than or equal to the partial derivative of the entropy S with respect to the pressure P times dP. This indeterminacy also indicates that in order to determine the entropy production while the state of a given amount of ideal gas changes, two of the three state variables of the gas have to be fixed. Now the first two laws of thermodynamics can be formulated as follows. The first law states that the energy of an isolated system is constant, whereas the second law states that the entropy of an isolated system can only increase or remain constant. The principle of entropy production determines the direction of processes in nature by forbidding such processes in an isolated system which would reduce the entropy of the system. The free expansion of an ideal gas demonstrates this fundamental antisymmetry in the direction of processes. The reverse direction of such a process is impossible in nature. That is, a spontaneous reduction of the volume of an ideal gas in a vessel is forbidden by the principle, because the entropy production was negative in the process. Some scientists, like Benjamin Thomas, Helmholtz and Canon Georges Lemaitre, draw a cosmological implication of the principle and formulated the theory of heat death, stating that the Earth or even the universe would unfit for habitation of human within a finite period of time. Helmholtz assumed that the universe in a continuous thermodynamic process will eventually reach the state of maximum entropy, where all the available energy will have been expended and no more activity will occur in the state of eternal rest or heat death. After the introduction of the Big Bang theory with a continuous expansion of the universe from a primordial singularity, Lemaitre rephrased this assumption by stating that the expanding universe slows down, becomes more diffused, and it will eventually reach the state of maximum entropy, which is a final equilibrium state of heat death. From the standpoint of modern physics, this conclusion is incorrect. First of all, the principle of increase in entropy holds true only for closed and finite systems. Furthermore, the second law has a probabilistic nature describing the probable course of events, from which deviations are possible even if only with a small probability.